Calculation of size tolerance. There are standard tables for tolerances to determine limits for size of mating features. Allowance difference between minimum hole size and maximum shaft size are available. Inch-based limit and fit values are defined in a standard that's been taken over by ASME, but it hasn't changed since 1967. It was originally a mil spec that was spun out as USA SI, and then its designation under that was B4.1-1967. ASME took it over in 2009, so that is the current standard, but the content has not changed. The metric limit and fit values, also defined by ANSI, which has been taken over by ASME in 2009, was defined in 1978, hasn't changed, and it's a B4.2-1978 was the original spec. And apparently they're working on revisions of the standard or in progress, but it's been a while, so it seems like they should be revising this. Tolerance system and terminology. A basic hole system and basic shaft system exists. It's based on the design application. The basic size is the value allowances and tolerances applied to calculate limits of size for the application. Nominal size is the size which a feature is known, but it may not be the actual size of the value. So I mentioned a 1/4-20 bolt. Its nominal size is a 1/4 inch, but if you measure it and to make it, you have to use a more accurate system than the fractions. Okay, basic hole system. This is the preferred system for calculating size limits for mating hole and shaft. Limits of size for the hole is calculated first, preferred when two mating parts simultaneously designed within one company. It also is used when the shaft design to mate predefined hole sizes. And it's good practice to consider the hole sizes achieved with standard tool dimensions. So that's why you would start with the hole. There are standard drill sizes. And if you can make your tooling to standard drill sizes, then and then make the shaft fit, you're not getting special tooling to make the holes. And it permits the use of standard tools to produce hole features. Now there's the basic shaft system that limits the size of the shaft are calculated first. And it may require non-standard hole sizing to meet special processes or tools that can increase costs. And used when a hole is being designed to mate to predefined shaft size. So you can buy these shafts that meet these standards and then design your product around them. The shaft is purchased and the mating hole must be specified. Calculating size limits using these standard tables. So the tolerances and allowances are organized in the tables and categorized according to type and class of fit. The function of the parts must be considered before using this table. The descriptions of general applications for fit type are provided in the Machinery's Handbook and in the standard ASME B4.1, but it's just republished in the Machinery's Handbook, which is a much more convenient resource. I recommend if you're going to be in mechanical design or machining or sheet metal in those areas, that you purchase a copy of the Machiner's Handbook, and it is available in digital format. There's the first type of fit called the running and sliding clearance fits. There are 9 classes of fit, and they're labeled RC1 through 9. They always provide clearance between a hole and a shaft. Parts move freely to vary the degrees according to the class of fit used. The smaller RC class, RC1, provides less clearance than the larger class, RC9. The amount of clearance permitted by RC classes of fit are proportional to the size of the tolerance of the feature. So if it's bigger diameter, you're going to apply different tolerances in a smaller diameter, and the chart tells you the ranges. Now the next type is location clearance fits. There are 11 classes of fit, LC1 through 11. They're used for locating parts that must assemble without interfering between them. So if you have a part that has dowel pins in one half and slip fit holes in the other, like many engine parts do, to align them, and then they're just used for alignment, but you don't want them interfering, and then you use fasteners like bolts to hold the parts together. So two different purposes of the hole patterns. These are for location features. Okay, the smaller clearance means less freedom of movement between two parts. LC1 is a very small amount of clearance. LC11 is a large amount of clearance, and it's not intended for parts that move after assembly. So you're just locating them, but you don't expect them to pivot, slide, that kind of thing. They may stick together fairly well, but you can get them apart. We then have our location transition fits. There are 6 classes of fit. There's LT1 through 6. They locate parts when slight clearance or interference is acceptable. LT1 is more likely to result in clearance. LT3 is about an equal chance for clearance or interference, and LT6 is more likely to result in interference. So again, you're going to put these things together, you're going to locate them, and you don't plan on taking them apart very often. Okay, there's location interference fits. There are 3 classes of fit, LN1 through 3. They locate the parts when clearance fit is unacceptable. They press fit to ensure no freedom of movement. LN1 provides the least interference fit. LN3 provides the most. It is an interference fit, so once you put them together, you got to press them apart or drill something out, but they're not intended for transmitting load. They're just for locating parts. Now we have the force fits. These would be for rotating parts, transmitting power. There are 5 classes of fit. FN1 through 5 all result in an interference condition. Each fit provides a consistent bore pressure throughout a range of sizes. The amount of interference between shaft and hole varies proportionally to the basic size, and tolerance is relative to small to prevent large variations in bore pressure. So very tight tolerances on these. Okay, limit calculations using tables. Select the category of fit first, then select the class of fit from the category. So how much fit tolerance you want. Then you find the appropriate table in the standard or book or reliable reference book, which would be the machiner's handbook, and locate in the table the nominal size range of basic size of what are the features you're designing. And you can obtain the tolerance values for that class of fit and select a nominal size range based off the table. And then you calculate the tolerance limits for the hole and the shaft. So let's look at an example here. This is an example of a portion of one of the tables under B4.1 tolerance table. This is taken from figure 4-56 in our textbook, but if you wanted to see the entire thing, you need to look at either the standard itself or the machiner's handbook. There's the theme here. Okay, so in this example, we're showing the tolerance ranges for a class RC6, so that should be something you're designing to move back and forth and not interfere with each other. And they even go as far as the hole and shaft have letter designations, and you have different diameters on the left. So if you're going to use something that's between 400 thousandths and 710 thousandths in diameter, you would use the first row of numbers. And if it's larger than 710 thousandths up to an inch, 190 thousandths, you would use the second row of numbers for your calculation. if you were to purchase an item like a gear with a hole in it and you wanted to use this system, you would order an H9 shaft. I'm sorry, H9 item with an H9 hole in it. And if you wanted a shaft that met this standard, it would be an E8 shaft. Okay, so here's an example of calculating limits of size. So taken from that chart, we're using the second row. Our basic size is 875 thousandths, so we know that needs to fit in with the range. Okay, so we want a RC6 class of fit, and so we're going to go off the second row because that's our number fits within 710 thousandths and 1 inch 190 thousandths. It's going to give us a minimum clearance of 1,006 tenths and a maximum clearance of 4,008 tenths. The hole needs to be toleranced 8750 plus 2 thousandths minus 0, and the shaft needs to be toleranced at 875 thousandths minus 1,006 tenths to 2,008 tenths. So if we go down to the bottom and look at our calculations, we calculate a maximum hole size of 877 thousandths in diameter, and our basic size, because it's 0, is going to be 877. And then our shaft, we have to do two calculations. We're going to subtract 1,006 tenths from 875.0. It's going to give us our larger size, which is 873 thousandths 4 tenths. And then from our basic size, we're going to subtract the low of the tolerance, which was 2,008 tenths. And that gives us the low of 872 thousandths 2 tenths. There will be exercises like this throughout the course, so you're going to need to review this type of slide and review how these tables work. Okay, so your basic size of mating parts and the values from the tolerance tables. Okay, limit calculations when one design exists. Limit calc, it occurs when one part is purchased from a supplier. You have to request documentation from the supplier to determine the part's limits of size, as you don't want one batch of parts fitting and the next batch doesn't. And you calculate the limits of size for the mating features. Okay, now ASME rule number 1. Y14.5 rule number 1. In a nutshell, any dimension of a regular feature of size must have a perfect form or shape when it's made at maximum material condition. Maximum material condition size at which most of the material is on the feature. So if you're making something, it's a condition where it's every single tolerance is at the maximum amount of material on the part. If you think of it as you machined a part and you put it on a scale, it's the maximum it would ever weigh. It would be that condition. It establishes a perfect boundary at MMC. Variations on feature size may not violate that boundary. A feature may not be perfect at least material condition. So that's where the part has the least amount of material on it. Okay, so that's rule number 1. The exceptions to rule number 1. Does not apply to stock shapes and sizes, so material sizes that you receive from a vendor. Other exceptions invoked by applying tolerances or modified symbols. So if you've intentionally modified it, then it's an exception. Geometric form tolerances to control straightness or flatness or derive axis or derive center plane on a feature of size. and its independent symbol to a size dimension, and geometric tolerances with a free state modifier to a feature. So it's an unconstrained state, not clamped down. Interrelationships. Rule number 1 does not require perfect relationships between features, the rule itself. Only force perfect interrelationships if part function requires a high level of control. ASME Y14.5 rule number 2. Regardless of feature size, or RFS, is applicable for all tolerances unless otherwise specified. Now in the previous versions you had to specify either RFS or a symbol in the geometric tolerance that was an S with a circle around it. Now it's just implied that if it doesn't have any symbol modifier, RFS applies. Applicable where no material condition modifier is shown, and regardless of material boundary, applicable for all datum feature references unless otherwise specified. So RFS applies to the feature you're making. RMB applies to the datums that are referencing those surfaces. Dimensioning for industry. Datums and tolerances establish allowable variation in required relationships. Size and location specification primarily requirements for dimensioning and tolerancing models and orthographic views. Apply dimensions and tolerances with consideration to the part's use. And revisions may occur after the product definition is released. Be careful. Application keeps those changes to a minimum. Interchangeability. So parts are able to be installed in a place of another part produced by the same requirements. So that is the cornerstone of American manufacturing. They credit Eli Whitney with inventing interchangeable parts, although that's debatable. Okay, ensured by a careful analysis of dimension tolerances. Interchangeable parts are typically preferred, with some exceptions, and it reduces the assembly time, spare parts cost, and maintenance costs. The other method is called mated parts, are sometimes a better option if only a few assemblies are needed. But once they go together, they're mated to unique parts and may not be interchangeable. There is a one car company that still operates under this type of regime, and it's Rolls-Royce, where they make parts to fit their own parts. So if you need to get a part for your Rolls-Royce, it has to be made to your Rolls-Royce or it won't fit. Okay, inclined and skewed features. Tolerance zones affected by a dimensioning method. Angles dimensioned with angle dimensions or locating edges. Angles and locations are somewhat open to multiple interpretations unless geometric tolerances are applied. And applied practices are form, orientation, or profile tolerances are used to control inclined or skewed features. Surfaces with an angle dimension. Angle defined with a dimension and tolerance in degrees has a wedge-shaped tolerance zone. The zone has a point at the location of the angle vertex. Produced surface must be within the tolerance zone. The surface form requirements are smaller near the vertex than at other locations, the way this is measured. Surfaces with dimensions to edges and corners. The location of the two edges of an inclined surface creates a tolerance zone for each. Each edge must be within the allowable tolerance. Location. And boundaries extended across extremes of two zones establish areas where the surface may lie. and it does not communicate flatness requirements necessarily. So if you need it flat, you need to make sure that you denote that. Arcs. The arc location has an effect on a radius tolerance zone. Arc located between tangents. Two boundaries are created by a radius tolerance tangent to projected surfaces. The radius can be located by dimensions to an arc center where two concentric boundaries are created. The center of the two boundaries may float within the location dimension tolerances, which can become ambiguous, but it also moves with the profile. So by controlling tolerance that way, it makes blending of radiuses more effective. And with modern CNC equipment going around profiles, it's the preferred way to dimension.